So let's go to chapter 2, okay? Shallow foundation or bearing capacity and settlement. So the lowest part of the structure is generally referred as a foundation. Its function is to transfer the load of the structure due to the soil on which it is resting. A properly designed foundation is one that transfers the load throughout the soil without overstressing the soil. Overstressing the soil can result in either excessive settlement or shear failure of the soil, both of which cause damage to the structure. Thus, geotechnical and structural engineers who design foundation must evaluate the bearing capacity of soils. So here, these are the three modes of failure for the soil. Okay? The first figure is the general shear failure. So a continuous failure surface develop between the edge of the footing here, between the edge of the footing and the ground surface. This type of failure is characterized by heaving. Where's my cursor? Heaving. Heaving at the ground surface accompanied by tilting of the footing. Okay? Meaning it can be moved here or here. Okay? It occurs in soil of low compressibility such as dense sand or steep clay. So, here, the general shear failure occurs when when the soil has low compressibility, and also if this one is on top of a dense sand or steep clay. So, if we look at the relationship between the load unit area over settlement, okay, uh, there will be a time that you will achieve QU. Okay? This QU is the ultimate bearing capacity. Then ultimately it will reduce. Okay? In this curve, it will be direct relationship between the pressure and the settlement. So as you increase the pressure on the soil, there will be equivalent settlement. Okay? So for this one, this is local shear failure, a condition where significant compression of the soil occurs, but only a slight heave occurs at the ground surface. So the difference between the two, here, the heave is too much, here is less. Okay? Tilting of the foundation is also not expected. Means movement here or here is not expected. This type of failure occurs in highly compressible soil, and the ultimate bearing capacity is not well defined. So the local shear failure, letter B, will happen only for a very high compressible soil. Okay? Letter C. This is called the punching or, punching shear failure. This condition occurs where there is relatively high compression of the soil underlying the footing. So meaning, this soil that supports the structure has very high, relatively high compression. Okay? So there will, if that is the case, look, there is no heaving of the soil, nor tilting of the foundation. So large settlement is expected without a clearly defined ultimate bearing capacity. Punching will occur in low compressible soil if the foundation is located at a considerable depth below ground surface. So we have here the empirical formula. So based on the experimental result by Bisick 1963, he proposes a relationship for the mode of bearing capacity. And it states like this, that the nature of failure of soil is a function of the depth, relative density, the ratio of the depth and width, and of course, the ratio of the width and the length. Okay? So ultimate bearing capacity, this is the width of the footing, QU, okay? Then depth of the foundation, Q is equal to gamma dF. Gamma is the density of the soil times the depth of foundation. This will be the pressure. Okay? Of course, you have also pressure caused by the weight of the structure here. Gamma C prime is the cohesion. Delta is friction angle. So based on the experiment, the failure zone under foundation can be separated into 3 parts. Okay? ACD, ADF, and AFH. And from this, of course, you just have an advanced reading about the formula and how it was created, because I will go detailed on the formula. So for strip foundation, QU is C prime NC plus QNQ plus 1 up gamma B and gamma. This is the formula for strip foundation. NC, NQ, and gamma is the bearing capacity factors that are non-dimensional and are only functions of the soil friction angle. Okay? For square and circular, these are the formula. Just read it. Huh? Square, circular, okay. So this is the table. So there is modification to Tersaghi. Okay? What is that modification? So for modification, these are the factors. NQ, NC, and gamma. But the same, we have table. Okay? We have table to use this one. So this is the formula for modified Tersaghi bearing capacity. What is this FCS, FCD? These are the shape factors, the factors, load inclination factors. Of course, this is the table. So the net ultimate bearing capacity is defined as the ultimate pressure per unit area of foundation that can be supported by the soil in excess of the pressure caused by the surrounding soil. So if the difference between the unit weight of the concrete used in the foundation and the unit weight of the soil of the foundation is assumed to be negligible, then QU net is QU minus Q. So these are the formula to determine the factors. So modification of bearing capacity for water table. Okay. So this is the figure. With B, depth of foundation. D is the depth of the bottom of the foundation to the groundwater table. Okay. Imagine this one, huh? So for case 1, if the water table is located so that D1, huh, is more than 0, means D1 is more than 0, means somewhere here. Okay? But less than DF. So if D1 is between from this point to this point, it is called case 1. Okay? If D1 meaning if the groundwater table is found between the bottom of the foundation or bottom of the footing to the ground surface, it is called case 1. And what will happen in case 1? Your effective surcharge Q will be D1 gamma plus D2 gamma sat minus gamma water. Okay? So here, the formula is the same for Q. Here. And also here. We are changing only the value of Q and the value of gamma. Q and gamma. If we are talking about water table. Okay? For case 2, For case 2, the groundwater table is located at a d distance from the base of the footing. So meaning D is more than 0, but less than this B. So for example, if the width is 2 meters, your D should be less than 2 meters. In able, we consider that it is under case 2. Okay? The factor gamma in the last term of the bearing capacity equations must be replaced by the factor. Now, case 3, when the water table is located so that D is more than B, the water will have no effect on the ultimate bearing capacity. Case 3 is if D is more than B. Okay? So, let's solve this problem. A square foundation is 2 meters by 2 meters in plan. The soil supporting the foundation has a friction angle of theta, 25 degrees. Cohesion is 20 kilonewtons per meter squared. The unit weight of soil is 16.5. Determine the allowable gross load on the foundation with a safety factor of 3. Assume that the depth of the foundation df is 1.5 and that the general shear failure occurs. Okay? So, theta is 25 degrees. What will be the value of NC, NQ, and N gamma? Okay? 25 degrees. 25 degrees. NC is 25.13, NQ is 12.73, and N gamma is 8.34. Take a look at the problem. It's correct. Okay? Now, since this is a square, this is the formula. 1.3 CNC plus QNQ plus 0.4 gamma B and gamma. Okay? So, by substituting all the values, 1.3, 20, the value of QU is 1078.29 kilonewtons per meter squared. Okay? So, the question here is determine the allowable gross load. Meaning, allowable gross load meaning we are talking about a unit of force which is newtons or kilonewtons. This is load. Okay? Remember that factor of safety is ratio of Q ultimate over Q allowable. Okay? Is it clear? Factor of safety is a ratio of QU over Q allowable. QU, we already solved it. 1079 divided by factor of safety divided by 3 is 359.5. That is the value of Q allowable. Okay? If the question is determine the allowable pressure with a safety factor of 3, this is already the answer. But the question here is allowable gross load. So, big Q is pressure times the area of the foundation is 2 by 2. You have 1,438 kilonewtons. Next. Okay? Here, a square footing is shown in the figure. Determine the safe gross load with a factor of safety of 3. Okay? Here, class, okay, we cannot use this formula anymore because this topic will be under modification under water table. Okay? Because, look at the figure. There is water table. Okay? So here, what should be the case of this one? What is the case? Okay? Case 1, case 2. Case 3, D is very far, which is more than B. So, if the water table is located between the ground surface, and the bottom of the footing, it is what? Case 1. And what will happen if it is case 1? You need to change the value of Q and gamma. So the value of Q, D1 gamma plus D2 gamma sat minus gamma water. And gamma prime will be used. Gamma sat minus gamma water. Okay? So again, we are in case 1. So meaning, if it is case 1, you need to replace the value of Q and gamma. Q is already defined, is D1 times gamma plus D2 times gamma sat minus gamma water. And gamma is gamma sat minus gamma water. And the formula will be the same based on the type of the what? Type of shape, square. So this is the value. The original equations actually 1.3 CNC plus Q and Q, but C prime is 0. That's why it becomes 2 equation. I mean, these 2 only. Let's go back. See? This is the formula, right? But C prime is 0. So this is already 0. So this will be the remain, these 2. Okay? So we have different factors to be used. NQ and gamma, of course, you can check this one from the table. Okay? Where's the table? Use the table for modified one. 32 degrees. Sorry class ha. (32°), 23, 23.18, and 30.22. 23.18 and 30.22, correct, okay? And here, the factor FQS and FQD, FQS and FQD, this is the formula, okay? FQS, okay? FQS, this is shape factor, okay? FQS, so 1 plus B over L tangent P. Then, this is 1.625. For FCI, FQI, and F gamma I, it's equal to 1 because the load is directed. Okay? Directed is always 1. If the load is not directed, for example here, that is not equal to 1. Okay? I will discuss on another example. Okay? If the load is not inclined. Okay? Then, what else we need? We have already FQS. What is FQD? FQD is the depth factor. So, we need to check this one and this one. Okay? What is our phi? Phi is 32 degrees, right? 32 degrees, meaning it is more than 0. If it is more than 0, what will happen? It will fall under here. So, FQD now is 1 plus 2 tangent P, 1 minus sine P squared dF over B. So, we use that formula. This one, oh. And the value is 1.23. Then, F gamma S, what is F gamma S? F gamma S is still under shape factor 1 minus 0.4 B over L. 0.6. So, using the formula, here, we now substitute all the values of this one. So Q is 12.845. Sorry. We need to determine first the value of Q. Okay? Since we are in case 1 is D1 gamma plus D2 quantity gamma sat minus gamma water. This is Q, Gamma prime is gamma sat minus gamma water. We need to calculate this one first. Okay? Gamma 1 times D1, meaning 16 times 0.5. 16 times 0.5 plus D2 0.5 times the quantity of gamma sat 19.5 minus gamma of water 9.81. So D1 gamma, D2 gamma sat minus gamma water 12.848. Okay? Then using the formula here, substitute everything, we will come up with 700.54. Then the same process. Because the question here is safe gross load. You need to calculate first the Q allowable, then multiplied by B squared, 336 kilonewtons. Okay? So that is for today's class. So tomorrow I will continue with eccentricity. And of course, if you have some questions, just message me in my messenger or in my Gmail, Yahoo Mail, or in our MS Teams, especially if you don't understand some problems. Don't worry, I will add some more, another video, but this time, I will solve by myself using, of course, using pen and paper, and of course, I will make another video for that. Okay? So, thank you for listening and have a good time.